All right, so now that we've talked about general plane motion and how we can analyze the velocity for these rigid body objects that are rotating and translating as they're moving within a plane, we're going to talk about kind of our last part of this to wrap it up, and that's going to be acceleration. So we've talked about how to analyze these general plane motion problems through their velocity by using relative motion. So we could use relative motion to find the velocity. We could also use instantaneous center of zero velocity to find the velocities. And now we'll talk about accelerations. So a lot of times in these general plane motion problems, we'll have to go ahead and solve for a velocity first, or for an angular velocity, and then we can move on to our accelerations and angular accelerations. So we can use any of those methods that we had talked about before, and then we can do our accelerations to find anything any of these accelerations, angular accelerations that we're looking for something going through general plane motion. And what that looks like is if we take a derivative of that velocity function, right? So we were dealing with our relative analysis of our velocity. That was going to be VB is VA plus VB with respect to A. And if we take that derivative with respect to time for all of these, so just take them and say, all right, the derivative of that with respect to time, we'll get the accelerations. And so those accelerations that we're going to get are going to be our acceleration of B equals our acceleration of A. And then this derivative of VB with respect to A is actually going to give us two accelerations, right? We are going to have accelerations in two directions in both our normal and tangential directions. This A becomes A of B with respect to A, which does have both a normal and tangential component. So AB with respect to A, the normal component, or I'll do tangential first. That's just convention. So plus our acceleration of B with respect to A in the normal direction. And these are all things that we've seen before. As we talked about our rotation about a fixed axis problems, we had that our tangential acceleration was the angular acceleration times r, and in this case the radius would be that position vector of B with respect to A. And then when we did rotation about a fixed axis, we had normal acceleration, and that was omega squared, our angular velocity squared, times the radius, times our position vector, I should say, times our position vector of B with respect to A. For rotating about a fixed axis, it is usually the radius of the circle of whatever's rotating. For here in these general planar motion problems, it's going to be your r, B with respect to A, that position vector of B with respect to A. And so the long form of how we kind of see this written out is AB, so the acceleration of point B is going to be relative to the acceleration of point A. I just realized I wrote B up there. I meant to write A. So the acceleration of B is going to be the acceleration of A plus this tangential component, which is going to be our alpha, which is our angular acceleration, cross product with r of B with respect to A, where it works just like that the relative velocity. Relative motion velocity analysis that we were doing where we had omega cross r. Here it's the same thing where alpha is rotating and causing motion only in the k direction. So your alpha will be either a positive or negative k, depending on if you're going clockwise or counterclockwise. So if you're going counterclockwise here, then you're going then you're going to have a positive k value. And if you go clockwise, then you're going to have a negative k value. So it works exactly the same as all of those relative velocity problems. And then finally, for this normal component of the acceleration, We're going to have minus omega squared, which is just going to be the magnitude of omega squared. It's not the vector form. It's just the magnitude of omega squared times the vector of r of b with respect to a. So what we get here is this general form of our equation that we can apply to our general plane motion problems when we're trying to find acceleration. And again, it's going to work a lot like those relative velocity problems that we had seen, usually just with a few more steps. And by that I mean, again, you usually have to find the velocities you need first, or specifically this angular velocity term, right? Typically this angular velocity may not be given, and you'll have to use your velocity equations to find that angular velocity, and then you can import it into our acceleration equation and continue solving from there. But otherwise, it's going to work just like those relative velocity problems that we had done, where what we'll do is we'll draw a kinematic diagram of how those accelerations kind of look, and then separate everything into the I and j components and solve for those two equations that we get. So that's typically how we'll go about solving these problems. So just as a quick rundown of how to solve is we're going to draw a kinematic diagram showing kind of your directions of your acceleration, as we've done in problems before. We'll find any velocities or angular velocities as needed. If something's not given and we need it for this calculation, then we'll calculate any of those. We can use, instantaneous centers of zero velocity or the relative velocity method to find those. And then we will set up equation with our Cartesian vectors. So that's our I, j, k. So that way we can then separate out our I equation and j equation into two equations. And from there, usually we'll have two unknowns, and we'll be able to solve for both of those. And those unknowns are typically going to be your acceleration of b and your angular acceleration. Those are typically the unknowns. Sometimes you may be given, the angular acceleration and you don't know the angular velocity, or maybe you're given acceleration of b and you need to go find acceleration of a. Things could swap around a little bit, but those are typically the things that we're finding in these problems. But we'll go ahead and work through an example or two so you can kind of get a feel for how this works. All right, so let's take a look at this first example, and it's going to be a nice, big, comprehensive example of our relative velocities and instantaneous center of velocities and our acceleration that we're learning here in analyzing this general plane motion. So in this example, we have rod AB that's confined to move along the inclined planes. If point A has an acceleration of 3 meters per second squared and a velocity of 2 meters per second, both directed down the plane at the instant the rod is horizontal, determine the angular acceleration of the rod at this instant. So before we do really anything, we'll kind of just look at the diagram and understand what's going on, and then maybe I'll draw our kinetic diagram too, to kind of better understand the motion of what's actually happening. So we have two 45-degree inclined planes on either side, and AB is completely horizontal. It's 10 meters long there, and we can see that VA and AA, so that velocity and that acceleration there of point A, are both straight down that incline. And so if we go ahead and write out, let's just write out our acceleration equation, the one that we know is our base we're going to start using. We're trying to find that acceleration of B, so we'll need the acceleration of A as a vector. It's like, okay, we could find that. We know acceleration of A is going down the plane. That should be pretty simple to deal with. It's just a 45-degree angle. And then our next components, we've got our alpha, our angular acceleration. We know we're looking for that. That's what the question asked for. We know we don't have that. And that is cross product with our r of b with respect to a. So if we kind of make a mini diagram just below it so we can kind of see my markups a little bit better. But we're going to have from a to b, that's our r of b with respect to a. That's pretty easy to find as well. Our VA is down this 45 degrees, so this is VA. It's also the same for our acceleration of A. And then if I continue on my equation here, minus omega squared times RB with respect to A. So that omega squared, we get there and we say, oh, well, that's probably going to be a problem because I don't have omega. I have no idea what that angular velocity is. So I'm going to have to go back to my velocity equations and figure out what that is before I can really manipulate this, because otherwise I'm going to have three unknowns, right? I don't know what AB is. I don't know what my acceleration or my angular acceleration alpha is, and I don't know what omega is. So having these three unknowns is not not how I want to start this. I definitely want to see if we can get that angular velocity first, and then try to find those angular acceleration and then our regular acceleration of B, which I suppose I don't need, but I'm probably going to solve for it just in the solving of this equation. All right, so let's think back to our last few videos and our ways to find velocity. And just to give you like a comprehensive view of this problem, I'm going to do it both ways. So we'll work through this by using relative velocity first, and then we'll work through it using instantaneous centers of zero velocity, just so you can kind of see both of them side by side and how they can interact with this acceleration problem. So first, I'm going to do, so let's just say this is option 1. You could find omega using relative motion velocity. So using relative velocities, we can find omega. So I'll go ahead and finish out this kinetic diagram that I started drawing over here, where we had VA and AA and then our R of B with respect to A, because when we do those relative velocities, we're going to use a very similar setup to this acceleration. Right, we've seen this before. VB equals VA, VA plus omega cross R of B with respect to A. So I'm just going to make an assumption that my bar is rotating in this counterclockwise fashion. Right, and it kind of looks like B is moving like that. We can kind of see this this bar is horizontal, and then we can see the ghost of where it's going to be, this like lighter version in the background showing us how it's moving. So it looks like that rotation, the way that B is moving with respect to A, it looks kind of like it's rotating around in a counterclockwise way. So I'm going to assume that that's the way my omega is going. I'm also going to assume this is the way that alpha is going. This is where my angular acceleration is going to when we get there. We don't have to be there yet, but when we get there, I'm just going to assume it goes the same way. And then the last thing I'm missing on this diagram is VB. And so my VB, since I know this movement is constrained, it says it has to be, where is it? First line there. AB is confined to move along the inclined planes. I know that it can only move up or down this plane here. Draw that a little clearer, right? It can only move up or down the plane there. And since A is moving down the plane, the only way B can move is going to be up the plane. And so it's going to be VB is up the plane by this 45-degree angle. And this is also a 45-degree angle on this side. And so with that, I can go ahead and see if I can solve for VB and omega. So my VB, if I separate that out into its components, that's going to be VB cosine 45 I hat plus VB sine 45 j hat. Right, that takes care of my x and y components for VB. That's going to equal VA, and I did not give myself anywhere near enough room for this. Let me just move that over. Let's just pop that over there. All right, so we've got the VB side of the equation. Now we'll do our VA. It is in the positive x direction, and VA has a magnitude of 2 meters per second. So that's going to be 2 in the positive x direction, 2 cosine 45 I hat, and then it's in the negative y direction, so minus 2 sine 45 j hat. That's entirely my velocity of A. Then I've got plus omega. I don't know what omega is. I'm trying to find it. I do know that it's in the positive k direction because it's going counterclockwise. Right, so by right-hand rule, that is plus omega times k hat, cross product with r of b with respect to a. And r of b with respect to a, since this rod is horizontal, it said that AB is horizontal and it's 10 meters long. That means that it is just going to be 10 I hat. Right, easy enough. It goes from A to B, it goes in the positive x direction. So that one's, you know, our easiest vector here pretty much. So now, if I do that cross product, this is a pretty easy one. It should be 10 omega, and then I know my shortcut for k cross I is j hat. And so now I can go ahead and just separate those out into their I and j components and solve for each one. So I've got, for my I components here, VB cosine 45 equals 2 cosine 45. Nothing. Nothing. There's nothing else. It's just the j hats. So that might be the easiest equation we've seen so far. That tells us that VB is 2 meters per second. And that kind of makes sense to us, right? With the 45 degrees, with this bar being symmetrical, it makes sense that if VA is going down by 2 meters per second, then at this instant, B would be going up the incline by 2 meters per second. And then if we take a look at those J components, now we've got VB sine 45, of course knowing that VB is 2. So VB sine 45 equals negative 2 sine 45 plus 10 times omega. So if I move that over to the other side, I'm going to get 4 sine 45 over 10 equals omega. So my omega, that angular velocity from the calculator, is 0.283 radians per second. And so again, the reason why I had to go through all of this is because I know that I'm going to plug him in up here. Right? So I know that up there I'm going to have my 0.283 radians per second in that acceleration equation. I'll put that up here just for reference. 0.283 radians per second. But just to show you that, you know, this isn't the only way to do this, we could also have done this by instantaneous centers of zero velocity, just as another example. So option 2, and you don't have to do both of these, you only need to do one of them. But option 2 is to use instantaneous centers of zero velocity, as we've kind of discussed, in our last couple of videos, where we have this rod AB. We have those velocities again, so we know that VA moves at this 45-degree angle downwards. VB moves at this 45-degree angle upwards. And then we find where they intersect, right? Where the lines perpendicular to those velocities intersect. So if I draw a line out perpendicular to VA, and a line out perpendicular to VB, where they intersect is that instantaneous center of zero velocity. And if I go ahead and look at this, I can see that with this right angle here, in order to make this a perfect straight line, right, our AB is on a perfect straight line, if I do 180 minus this 90 minus this 45, it's going to give me this angle over here. So that's 180 minus 90 minus 45, which is just 45. And I can see here, I know this overall, VA makes a 90-degree angle here, and I know this portion is 45 degrees, which means that this portion right here also has to be 45 degrees. And then if I look at the triangle that I have left, I've got a 45, which means this has to be a 90, right? All of our triangles always add up to 180 degrees. So I've got a really, really nice, easy triangle to work with for this instantaneous centers of zero velocity method. Because I know that my position vector from IC to B, so here's R of B with respect to IC, and here is R of A with respect to IC. And when I do this instantaneous centers of zero velocity, I can just do it in these scalar methods. So my VB is omega times RB with respect to IC, or my VA is omega times A with respect to IC. So in this case, I know what my VA is. My VA they gave us was, I know it, I already forgot it though, 2. And I know that the length of this rod here, this was 10 meters. So I can find this RAC really easy. My RAC here is going to be, let's see, 45 degrees. So that's going to be sine 45 equals, is it sine is opposite over hypotenuse. So sine is opposite. So RA with respect to C over hypotenuse is 10. So my RA with respect to IC is 10 sine 45. Right, that's just from the triangle geometry. That's all I was doing to find that position vector. And it's not even the vector, I'm just finding the magnitude of this because we do this IC all in the scalar form. So that's 7.07. And with that, I could have done it for B, but I did it for A here because I know what that VA is. So I can rearrange this so that omega is VA over RA with respect to IC. VA we know is 2, and our RA with respect to IC is 7.07. So that tells us that the magnitude of our angular velocity is 0.283 radians per second. So I know sometimes when you're working through these problems and like as you're learning how to do relative velocity, how to do instantaneous centers of zero velocity, it's kind of hard to see when one could be easier than another or the differences between them. Truthfully, they're going to get you to the same place. You can do whichever one you feel more comfortable with. But in this case, it was a little bit easier to do that instantaneous centers of zero velocity, in my opinion. I mean, it was just a little bit shorter. We got to the same place either way, so you can do either one. And now that we have this, right, we got that exact same omega. Now that we have that omega, we can go ahead and do what this problem asks for. We can do this new stuff of trying to find that angular acceleration there. And so the approach is going to feel a lot like option 1 here, right? Instantaneous centers of zero velocity is more like a really handy shortcut, a really handy thing you can do to make your problems a little bit easier when you're finding velocity. But there's not really an equivalent for it for the acceleration. Your acceleration you're going to do with your relative motion. So we're going to go ahead and set this up now for our angular acceleration. I think what I'm going to do, I'm going to get rid of all of this and then just move this relative velocity stuff down for reference. But we don't really need it. We'll just kind of keep it down there in case we want it for later. And let's draw ourselves a new kinetic diagram just for acceleration this time. So we know on our bar, we know our acceleration of A down by 45 degrees. Acceleration of A is 3 meters per second squared. We know our angular velocity now, 0.283 radians per second. And we're just going to assume this angular acceleration goes the same way. And then for the acceleration there at B, it's actually going to go in the exact same direction as our velocity as well. Because AB is moving on these straight line paths, right? There's no like curvilinear motion. There's not something that is normal to the path, right? Not on our straight line motion. It's not moving through a curve. It's just accelerating up on this straight line path on that plane there. So there's not like a component of acceleration this way. There's only this acceleration along the path. All right, so we've got an acceleration, again, at that 45-degree angle, moving along that path that it's constrained to. So now that we kind of have a diagram and have a sense of direction on all of these things, oh, and of course our RB with respect to A. RB with respect to A is still the same. It's going to be 10 I hat. Now we can go ahead. Now we have everything. We can go ahead and start plugging things in and see how far we can take this acceleration. So our acceleration of B, we'll break that into its components. We've got AB cosine 45 I hat plus AB sine 45 J hat equals, and then I'm going to have to drop a line and we're just going to go do A. So our A is 3 cosine 45 I hat minus, because it's in the negative y direction, 3 sine 45 j hat. So that was our, we'll just go ahead and kind of mark these things as we get them done. So we've got B, we've got A. Next we'll do our alpha term. So alpha is going to be in the positive k direction, right? Because it's going counterclockwise. So alpha k hat cross product with our r vector, which is 10 I hat. and then minus, we've got this term, and finally this last term here is omega squared times r BA, so our omega squared, again, this is just in a scalar form, it's being squared. So this is just the magnitude, 0.283 squared, times the vector of 10 I hat. And then we're going to do just as we did down here. We're going to write everything out, and then we're going to separate it into the I and j components and solve for our angular acceleration. If I write everything out, I can do this somewhere right. I don't know that I have enough room. That's okay. AB cosine 45 I hat. You know what, I'm not gonna write this all out again. I'm gonna write just this, everything to the right of the equal sign I'm gonna write out again so I can simplify this stuff down here. So equals 3 cosine 45 I hat minus 3 sine 45 j hat. And then I have k cross I, which is going to give me a positive j. So that's plus 10 alpha j hat. And then my last term there, I do minus 0.283 squared times 10, I have minus 0.8 I hat. Now I'll break it into those i's and j's. So I see I have AB cosine 45 equals, and then I'm taking from this last line here, 3 cosine 45 minus 0.8. And so there I can solve for AB. I get AB equals 1.87 meters per second squared. And then if I do those j hat terms, I'm going to get, sorry, I'm going to get our AB sine 45. And then that equals negative 3 sine 45 plus 10 alpha. So I can plug in right here 1.87 and then rearrange and solve for alpha to find that angular acceleration is 0.344 radians per second squared. And I got a positive value when I worked this out, so it means I did assume the correct direction for my alpha, right? It is going counterclockwise. Right, so these acceleration problems, they can be kind of long, they have several steps to them, but they really work in the exact same way that we did our relative velocity. It's just you have to be a little bit more cognizant of where the accelerations are going because it's not quite as intuitive as the velocities, since it has those normal and tangential components to it. Let's go ahead and take a look at another example. In this example, crankshaft AB turns with a clockwise angular acceleration of 20 radians per second squared. We want to determine the acceleration of the piston at instant AB in the position shown. Right, so at the instant shown, we want to find that acceleration of the piston up at C. In this position as it's shown, like in this diagram. So at this instant, our angular velocity of AB is 10 radians per second, and our angular velocity of BC is 2.43 radians per second. So first thing we'll notice is that we're given our angular velocities, right? And since we're given those angular velocities, we're actually not going to have to go through any of that stuff to find them, right? We're not going to have to do relative velocity or instantaneous centers of zero velocity, any of that, since we have these angular velocities for each of these two rods, we don't have to solve for them. So thank goodness that at least is going to save us some time there. And we can just go ahead and start and jump in on this acceleration portion. So I noticed that we have two rods this time. Instead of in our last example, we only had the one. We had AB. but this time we have both AB and BC. If we kind of look at what's going on here, I can separate them out if I want to. We could also leave them together, but I like to visualize them kind of as separate entities, where we have AB, there's A, and the first thing that we might notice when we break out this AB here is that A is fixed, right? A is a fixed location, so our segment AB is acting like rotation about a fixed axis. So this is a throwback to, a few videos ago. We don't have to use that, the general plane motion form, because it's just rotating about that fixed axis at A. And even if we did want to, the equations are very, very similar that you could probably figure it out either way. So even if you started AB by saying, all right, for AB, I'm going to say AB equals acceleration A plus alpha AB cross R B with respect to A minus omega squared R B with respect to A. So even if you use this general plane form, you would actually find, oh, there's no acceleration at A because A is fixed. And then this is actually just the exact same equation as rotation about a fixed axis. This is exactly how we found rotation about a fixed axis, our acceleration form of that, just a few videos ago. It's that exact same equation. So either way, you'd probably be able to figure that out. But let's go ahead and finish this kinetic diagram before I get too distracted here. So no movement at A. We know that there is, our velocity of B. Again, not needed. We really don't need it on this kinetic diagram. I might not even include it here just so we don't confuse ourselves. Maybe I'll just go ahead and only include those accelerations. So we have the alpha, we have angular velocity, AB, is 20 radians per second squared. They also gave us, in the same direction, omega AB as 10 radians per second. So that means that we have this guy, we have omega, R of B with respect to A. R of B with respect to A, that's going to be our vector from A to B. Back to A, and this angle here is a 45-degree angle. And this rod is 0.25 feet long, so we can find our RB with respect to A. All right, that's easy enough. We can find that. And that's all we need. Those are all of the ingredients that we need to find that acceleration of B. Now, notice that we don't really know the direction of acceleration of B. We do know that the tangential component of our acceleration, right, so AB will have a tangential component that goes out this way in the same direction as rotation. So we're rotating clockwise in this case, so AB is going to be moving clockwise, like moving to the right tangentially. But we also have this component that is along the rod, right? We have that normal component of the acceleration of AB because it's moving in that circular fashion, right? We've got that rotation about the axis, so it's going to have both a normal and tangential component to its acceleration, so that the overall acceleration is somewhere in here. And maybe let me use a different, I don't know if I have a better color for this to visualize it a little bit better, but our A, I'm just gonna have to move this, our acceleration is kind of in this ambiguous area between them. We don't know exactly what direction. We'll have to find it. Okay, so with that kinetic diagram, that'll help us a little bit with our AB. And we're going to want that acceleration of B for this BC portion. You can either do the BC diagram now if you wanted to kind of see it, get a little bit of a better sense of what it looks like. I think I might wait and go ahead and solve for AB. I guess, I mean, it really doesn't matter. We'll go ahead and do the diagram. We'll do this diagram so you can see all the diagrams there. So our diagram, again, you're going to have AB in some direction. We don't know yet. We need to find AB first. We're given this omega BC, 2.43 radians per second. And then we also know, if I move this back up so we can see our diagrams a little bit better, we know that our velocity for C and our acceleration at C is stuck in that piston, stuck in that like confined shaft. It can only move in two directions, either up or down, right? It's either a positive J or a negative J. And here with the way that these things are swinging, since my curve of my B with respect to A, B is moving to the right, it looks like, I'm going to assume that my acceleration of C is upwards. I'm going to assume that AC goes straight up instead of down in this shaft. And so that's what I'm looking for, right? I'm trying to find that AC, trying to find that acceleration of the piston there at C. And this is our general plane motion, right? We have the rotation happening and the translation happening at the same time. And I guess I could note this angle here. They gave us an odd little angle, 13.6 degrees. So with that, we know that we need to find this AB term in order to find this AC term. So let's go back to our equation for the AB section of the rod to find acceleration of B. All right, so our acceleration of B is going to be alpha AB, which we know is 20 radians per second, so 20, and then it's clockwise, so that's a negative k, so negative 20 k hat, cross product with the vector of RB with respect to A, so that is going to be, have x and y components to it, 0.25 sine 45 I hat, and that is in the negative x direction, so that needs a negative out front. And then in the positive y direction, so plus 0.25 cosine 45 j hat minus omega squared. Omegas they gave us is 10, so 10 squared, times RB with respect to A, and I am absolutely out of room for that. Let me not write that over here. Let's move that over. Minus 10 squared times negative 0.25 sine 45 I hat plus 0.25 cosine 45 j hat. All right, let's see if we can simplify that just a little bit. So I have a negative 20 times negative 0.25 sine 45. And that's going to give me 21.2. Is that right? Nope, that's not right. I am looking at the wrong thing on my paper. That is not the right number at all. Sorry. That is, from my calculator, should give me 3.53. That sounds a lot better. That sounds a lot more accurate. All of these are just going to give us numbers, right? All we're doing is we're finding what this AB is. There's no unknowns in here. It's just whatever AB is. So your negative 20 times negative 0.25 sine 45, that's going to give you 3.53 j hat. And then I've got a k times a j, so that's a negative I. And that's a negative I times a negative, so that's going to give me a positive. 20 times 0.25 cosine 45. And that is another 3.53 I hat. Then my 10 squared is going to be 100, and so that's a negative 100 times negative 0.25 sine 45 plus 17.68 I hat. And then I've got a negative 100 times 0.25 times cosine 45. Going to give me a negative 17.68 j hat. For an overall acceleration of b that I'm going to go ahead and keep. I'm going to keep in this Cartesian form. I'm not going to take the magnitude of it because I know I need to use this again in the BC rod portion. So for this AB, goodness gracious, if I could write a little bit better. Acceleration of b. We're going to combine those and get 21.2 I hat minus 14.14 j hat. So now I know that is my acceleration vector up here. Right, this AB is 21.2 I hat minus 14.14 j hat. So I did all of this work to find that so that I could find this acceleration of c. So I'm going to rinse and repeat, right? Just do this exact same process, but now for the BC section of the rod. So for BC, I'm going to have acceleration of c equals acceleration of b plus alpha BC. Cross product with r of c with respect to b minus omega bc squared times r c with respect to b. Alright, so let's pull out what I need here. And again, I am going to go from b to c, so that's r of c with respect to b. And as I can see here, it's going in this counterclockwise fashion. So I'm going to assume that my alpha does as well. Goes in this counterclockwise fashion. But I don't know what that is. It's not given to me. So they did give me the angular acceleration of AB, but not for BC. It's something that I'm just going to have to find. So my AC I know is only in the vertical direction. It's only in the positive j hat direction. I can go ahead and put that in here. AC j hat equals AB. And we just found AB. It's 21.2 I hat minus 14.14 j hat. And then my next section here, that angular acceleration of BC. Again, I don't know what it is, but I know that it is, or I'm guessing, I'm assuming that it is counterclockwise. So that's a positive k hat plus alpha BC k hat cross product with my position vector here. And that position vector is positive in the x and positive in the y, and it has this angle of 13.6. So the x component is sine 13.6. What's that length? 0.75 feet. So 0.75 sine 13.6 I hat plus 0.75, oh, not sine, cosine 13.6 j hat. And then finally our last term, omega BC, which they gave us as 2.43. So minus 2.43, I'm going to need more room for this, 2.43 squared times that same r vector again. 0.75 sine 13.6 I hat plus 0.75 cosine 13.6 j hat. Whew, okay, so I'm going to multiply all of that stuff out and then separate it to its I and j components and solve for my acceleration of c. So if I simplify all of this, multiply it all out, I'm going to get AC j hat equals 21.2 I hat minus 14.14 j hat. And then I have the alpha BC times the 0.75 sine, and I'm going to go ahead and simplify that to be a number. And k cross I is j, so that's going to be a plus 0.176 alpha BC. And then I'm going to simplify this as well, this alpha BCK times 0.75 cosine 13.6 j, so that gives me a negative 0.729 alpha BC j hat. No, not j hat, I hat. Yeah, sorry, I forgot my j hat on the last one. Whoops. J hat, and then this one, I guess I can just erase his little hook on the end. Now he's an I. Okay, and then we'll simplify this last guy here. So the negative 2.43 squared times 0.75 times sine 13.6, that gives me negative 1.04 I hat. And then the multiplication of all that last stuff is 0.43 j hat. Oh, there's a lot of numbers in there. Right, these acceleration ones get really long to write out. They're not horribly difficult, it's just a matter of keeping all of your signs straight and just making sure that you've caught all of those numbers, because it's going to take you multiple lines of writing to get all of these down, as you can kind of see here. Alright, so now I'm going to separate it into the i's and the j's, and I'm just going to move all this stuff that I had before. I really don't need this. And my I components that I have are going to be, let's see, I have none for AC, and then I just have the 21, whoops. Put that back in a little bit, there we go. Okay, so I have 0 equals 21.2. Let me see. I'm just going to circle these. Okay, so here's an I term. Here's an I term. Here's an I term. So minus 0.729 alpha minus 1. 0.729 alpha minus 1.04. And so that's perfect. I can solve this for alpha. Right, I can plug it into my calculator and get that alpha BC is 27.7 radians per second squared. And then for my j's, do this in a different color, j hat, I'm going to get AC. I've got AC negative 14, whoops, equals negative 14.14 j, not j, I don't need the j's anymore, I'm just taking the numbers, just the coefficients. So AC, I got the 1414, plus 0.176 alpha, and then minus 4.3. Right, so I can just take this alpha that I found, plug it in there, and I get that my acceleration of the piston at C is negative 13.5 feet per second squared. Right, so I had actually assumed the wrong way on this guy. I assumed that my piston was being pulled up, but it looks like it's being pulled down at this instant. Or that my acceleration is slowing down is another way to think of it. My velocity is going up likely, but my acceleration, it is slowing down. And so there's one where we didn't have to use any of that velocity, but we had multiple parts, multiple rods to kind of break down into different components to find those accelerations for. All right, so I've got one last example for you, but I really want you to take this one as kind of a practice problem. Try to pause the video and do it yourself before we work through it together. So it says that there is a collar at C that moves downwards with an acceleration of 1 meter per second, and that should be meter per second squared because that's an acceleration. So moving downward with an acceleration of 1 meter per second squared. At the instant shown, it has a speed of 2 meters per second, which gives lengths CB and AB an angular velocity of 10 radians per second for both of them. So omega AB and omega CB are both 10 radians per second. Determine the angular accelerations of CB and AB in this instant. So go ahead and pause the video here. Go ahead and attempt it on your own, and then we'll work through it together. All right, so let's go ahead and take a look at this problem. It's really not terribly different from the problem that we had just done in the last example. But the only difference is that instead of being given an angular acceleration at the beginning, you're actually given the acceleration at C at the end. So the last problem we were trying to find acceleration of C, here you're given acceleration of C and you're trying to find angular accelerations instead. So I'm going to draw a little diagram. And this time I'm just going to keep it all as one thing. I'm not going to bother to separate it out into AB and CB. I'm just going to keep it all as one diagram here. Wow, I really should learn to draw straighter lines, but for these purposes, this is what we got. All right, so we have B down here, we have A, and then we have that collar at C. So writing down some of the things that we notice here, we know that we're given this angular, the angular velocity, AB, is 10 radians per second. We know at CB it's also 10 radians per second. And so we're going to go ahead and just make the assumption that those alphas are the same, that those angular accelerations are in the same direction. Could be wrong, could be decelerating, could be going, the opposite way. But for now, this is a fine assumption. We can also see those lengths that were given there, of the 0.2 and the 0.2. And then let's see, we're also given this acceleration downwards. AC is 1 meter per second squared. We can also see that at A, there's no acceleration. Again, A is a fixed point, so that AB is doing a rotation about a fixed axis, while CB undergoes general plane motion. And then finally, we do know that B is moving, right? So we know that B is moving, it has an acceleration that, we may not be sure of the direction of, but it's probably out somewhere like this, since B is kind of swinging to the right, it looks like, based on how those angular accelerations are moving. And then, of course, put these in kind of as ghost vectors. We're going to have that vector of B with respect to A. And then we can also have that vector of R, C with respect to B, right, along each of those rods. So it's kind of a lot. That's why I like to usually break it out as kind of a lot of information in one diagram, but it can be nice to see it all together too. And so what we're going to do is we're just going to start working it out. We're going to start rod by rod, just as we did in the last problem, and just kind of see how far we can get. So we know for AB, we'll start with AB and then work our way to CB. We're going to have acceleration of B. And again, since this is rotation about a fixed axis, we can use that rotation about a fixed axis is alpha AB cross RB minus omega AB squared times RB. And that RB is the exact same as the RB with respect to A. Right, it's just the B from that rotational point of A. So you can write that either way. And again, no acceleration of A, since A is not accelerating. It's rotation about a fixed axis. So I can go ahead and start plugging some stuff in here. My acceleration of B is going to be, I don't know what my alpha AB is. That's one of the things I'm trying to find. I need to find that angular acceleration of AB and of CB. I'm just going to leave it as is for now and notice that it is going counterclockwise, so that's a positive K. Alpha AB K hat cross product with my vector of RAB, and I see that it is 0.2 straight downwards. So that's going to be negative 0.2 J hat. Minus, I was given that omega, so my angular velocity of 10 squared times that vector of 0.2 J hat, that position vector. So notice I still don't know what that angular acceleration AB is, but I'm just going to leave it like this because I'm going to go ahead and plug it in to the next equation that I have with CB when I go and do this CB breakdown. So let me simplify this just a little bit before I do that. I've got a K cross a J, that gives me a negative I. So that's 0.2 alpha AB I hat plus 20 J hat. And then I'm going to go ahead and do this whole thing for CB. Right, so a lot like the last problem, we did all our accelerations for one rod. Now we'll do it for CB. And so I'm going to have my acceleration of C equals acceleration of B plus alpha BC cross R C with respect to B minus omega BC squared times R C with respect to B. Perfect. So I can start plugging some stuff in here where this time I do know what that AC is. It is negative 1 J hat equals, and then I can plug in everything here from my AB, 0.2 alpha AB I hat plus 20 J hat plus my alpha BC. And let's see, what direction did I give that? I said that was going counterclockwise as well, so that's a positive K. The alpha BC K hat cross product with my RCB, and it looks like I have this. I have not the overall length of CB, but I do have the X and Y components of that position vector CB, so that makes things really easy for me. It's a negative X direction and a positive Y direction. So that's negative 0.2 I hat plus 0.2 J hat. And then minus omega BC, which was given as 10, again. 10 squared times negative 0.2 I hat plus 0.2 J hat. Oh my goodness, almost there, right? The only unknowns that we have in this equation now are our alphas. So it's just a matter of solving for those angular accelerations. So I'll simplify this out a little bit before we do that. Negative 1 J hat equals 0.2 alpha AB I hat plus 20 J hat. And then I have my K cross my I. So that's going to give me minus 0.2 alpha BC j hat, and then I'm going to have a k cross a j, that's a negative I. So minus 0.2 alpha BC I hat plus, because I've got negative 100 times negative 0.2 plus 20 I hat minus 20 j hat. Whew, okay. So for my I hat components, I'm going to have 0 equals 0.2 alpha AB. Where's another I hat? Oh, here we go. Minus 0.2 alpha BC. And then plus 20. And then my j hats, I have negative 1 equals 20 minus 0.2 alpha BC minus 20. All right, that makes things pretty easy. That makes my alpha BC 5 radians per second squared, which I can then plug back in right here and solve for alpha A. Whoops, that was not the right plug-in. Sorry, let's put that back. All right, we're going to plug in right here for alpha BC to get alpha AB, and alpha AB from the math there is going to give us negative 95 radians per second squared. So those are our answers. And we'll notice we did get a negative there for our AB, which means that we had assumed the wrong direction. Right? That's all it means. It means that our alpha CB is actually going this way. Right? It's actually going clockwise instead of counterclockwise. But I hope you were able to get that example on your own. That covers most of the types of problems that we're going to see with this acceleration, right? This relative analysis, very similar to our relative motion analysis of our velocity, just with a few extra steps, a few extra things in there, which will lead us to our one last topic related to this acceleration that we had in our relative motion velocity, and that was rolling without slipping. So in our next video, we'll take a look at our acceleration problems of rolling without slipping.